So is she not ready with that?
Alright, so last night I asked you to view a video assignment for just the beginning part of this last section of our unit. And I mean, it was only 12 minutes or so, not terribly long. But we're going to go over average value a little bit further. We've briefly kind of talked about this in a previous section, but we're going to just explore it a little more in this last section of the unit. So, someone messed up all my pens. It's not April 1st yet, whoever it was. All right, average value. Average value is related to this integral setup or concept that we've been talking about for some time. And I'm going to go back to just particle motion a little bit to kind of let this sink in, perhaps. Hey, Cole. Thank you. All right, so what we've been talking about in terms of the fundamental theorem of calculus is if we want to work backwards from a function, we can first of all take the antiderivative, like use that reverse power rule, and if we know the bounds, we can do top bound minus bottom bound. So if I want to work backwards from velocity, what would my antiderivative be? Position, okay, and I'm going to do position at time B and subtract our position at time A. Okay, this is our first fundamental theorem of calculus. Basically, it's saying that the area under velocity, okay, on this interval is equal to the change in position, aka displacement. We've used that word before. But we can relate this to any function. For instance, if I did the integral from a to b of f prime of x, so I would say the area under f prime is equal to what? Change in f of x, okay, the antiderivative. So this would be f of b minus f of a. Okay, so the area under any graph is equal to the change in antiderivative value. Okay, we've been dealing with that for some time. Average value, on the other hand, is a way for us to calculate the average output or the average answer from this beginning function that we have within an integral. So for instance, I'll rewrite this down here. The integral of velocity we know is p of b minus p of a. What would I have to do to the change in position in order to get a velocity unit or a velocity value? What do you think, Anush? Divided by some time value. So if you take a change, these are essentially a change in y values. You'd have to divide it by a change in x values, meaning the respective x's. So if I divide this side by b minus a, I'd have to divide this side by b minus a. And instead of writing it like this, because that's just a big integral and a big fraction, we instead write a coefficient out front, 1 over b minus a. So in order for us to find an average answer or an average output of a function, we're going to work backwards like we typically do, find that change in antiderivative, but we're going to divide by the difference of the bounds. So whatever the distance is between A and B. Is that helping with the connection? Okay. So for instance, I think we did it previously. If I wanted to find the average velocity, I now have two different techniques to help me do that. And which technique I use depends on which information I have. So what if I wanted to find the average velocity, but I know the position function? How would I find average velocity if I know the velocity function? We're going to find the same value, but the math, I guess, would be different depending on the information we have. Yeah?
If you have a position, you can kind of use the right side of the equal sign. Just plug in the
Right. Okay, so this is basically representing the slope between two position points. So if this is the slope between two position points, aka average velocity, then that should be the same as this side, which would be average velocity as well. So if we know position, we're going to find the slope between 2 points, okay, that beginning point and ending point. But if we know velocity, we're going to have to integrate velocity, but then divide by the difference of the bounds. Okay, they are producing the same output. It just depends on the math or the calculus that you use to help you get your value for average velocity. Now, in the video assignment last night, we kind of shied away from position and velocity and acceleration. We looked at more general functions, like didn't really have certain context to it. But we are going to take a look at some contextual problems today. So we can kind of think about, what does this number mean? What does this number mean? How can we decipher the differences? Okay, so I'm hoping that this is just a good understanding or a good visual of kind of clarifying what was going on last night. All right, so on page 400, we're going to take a look at this free response type question. A ski resort uses a snow machine to control the snow level on a ski slope. Over a 24-hour period, the volume of the snow added to the slope per hour, so volume per hour, is modeled by this equation S. If this is a volume per hour, then this equation is representing a rate. So this is your rate of snow being added. The rate at which snow melts is modeled by this function. So rate lost. Both S and M have units of cubic yards per hour. At the beginning of our calculation, the slope has 50 cubic yards of snow. All right, that's our beginning volume. Do you see how this one's kind of similar to the ones we were doing the other day? How we have this in and out or added or subtracted type deal? Okay, we're comparing two different rates here. Compute the total volume of snow added, okay, just added to the mountain over the first 6-hour period. So notice how we have the rate at which snow is being added. How can we utilize that rate to figure out how much snow was added? There we go. We're going to take the integral, because notice how this S of t is in units of cubic yards per hour. And if we want to just try to figure out volume, that means we have to get rid of that per hour on the unit. So if we're going to work backwards from a rate, that would do that for us. All right, so we're going to integrate S of t. And what did you say our bounds were, Anush? 0 to 6, the first 6 hours. So from the very beginning to time 6. All right, so this is why we're going to need our calculator. We're just going to type it in. Make sure you're in radian mode. since sine is being squared, it's a little different on how it's going to look on your calculator. You're going to type in sine of x divided by 14, and then after you close off that parenthesis, that's when you're going to hit the squared button. Okay, your calculator doesn't have the same notation as your paper does. It cannot put a squared after the sine function, so you have to put it at the end. Alright, so we'll get 142.413, chop it at 1, round it to 2, up to you. Units, if it's a volume of snow, yards cubed. Good. Alright, for part B, find the value of the integral from 0 to 6 of the m function, and also the integral from 0 to 6 of the m function, but multiplied by 1/6. Alright, so this is just going to be a little bit more calculator work for us. Math 9, 0 to 6. Let's see, m function 10 plus 8 cosine x divided by 3. We get 81.8231. How can we get the other integral value? Multiply by 1/6, yep. Or divide by 6, same deal. We'll get 13.637. Chop it 1, round to 2. Either one's fine. Alright, so using correct units, let's maybe put those in, and then we're going to explain what each one represents in the context of the problem. So, let's see, we worked backwards from the m function, which represented the rate at which we were losing snow or it was melting. So what do you think this 81 number represents? Okay, volume of snow lost, melted. Can we put a unit on it if it's a volume? Yards cubed. Alright, what about the 13 number? If you think about what we did, we took this yard cubed number and we essentially divided it by 6. Yeah?
The average volume lost?
It's not the average volume. It is an average though. What do you think, Christian?
Average volume lost per hour.
It's the average rate.
Okay, so the average volume lost per hour, or in other words, the average rate at which snow is lost. Okay, to help you think about this, whatever this m of t function represented, we're just going to put the word average in front of it. So notice how at the top it says the rate at which snow melts. So if we put the average in front of it, it'd be the average rate at which snow melts. That's our meaning. So, like you said, our units would be feet cubed per hour. Are we doing okay with the differences between the two? Okay. Is the volume of snow increasing or decreasing at time 4? Are we getting more snow on this mountain, or are we starting to get less snow on this mountain? How do you think we can figure that out? Plug it into what? Plug 4 into what? Yeah?
Second one, the M of T, that's like prime.
Okay. Let's plug in 4 into the m function. So 10 plus 8 cosine, and we'll have 4 divided by 3. We'll get 11.8819. All right, so if we think about our context here, this is the rate of snow melting. What else would be useful to know? The rate at which snow is added. So what if we plug in 4 into S? $23.682. Chop it at 2, round it to 3, either one. Okay. Rate of snow added. So all this snow on the mountain, are we going to keep getting more snow or less snow? Why more?
Because it's bigger.
What's bigger? You said it.
Like, there's more snow being added.
Notice the rate at which snow is added is more than the rate at which snow is melting. So if you're gaining more than you're losing, the total volume should be increasing as well. So we'll say increasing because rate added is larger than rate lost at time 4. All right. Can we figure out how much snow or the volume of snow that's on this mountain after 5 hours? What do you think, Christian?
Okay, I'm thinking on this one we do S of T plug into 5. That's how much will be added, and then you subtract it by M of 5.
If we do S of 5 minus M of 5, that's going to be this. So these are rates.
So you gotta do the area on the and then subtract.
There we go. So S of T, the integral of S of T minus the integral of M of T. What are our bounds going to be? 0 to 5. Okay. So our first integral here is amount added. The second integral is the amount lost. So if we subtract the 2, we're just going to find the overall amount of snow that was either added or subtracted in the end. Is there something else that would be useful to know if we want the overall volume of snow at 5 hours? How much you start with? How much do we start with? 50. And notice how that was at time 0. Let me ask you this. What if they told us at time 3 it was 50? We would change our lower bound to 3. Okay? So let's go ahead. It might take us some time, but we're going to type it in. So we're going to do 50 plus. You could type it in all at once if you want to do one at a time and then add or subtract them. That's fine. Let's see, math 9, 0 to 5, S of T, 24 minus see, 95.3353. And if this is the amount of snow, we'll have yards cubed. All right, last one. Suppose the snow machine is turned off at time 10. Write, but do not solve an equation that could be solved to find the time, we're just going to call it K, when the snow would all be melted off this mountain. Can we maybe think about in words, maybe, or perhaps like the last one, to help us get to what we're looking for?
Be the integral.
There's gonna be some.
10 to k, right?
Uh-huh. Why 10? Why k?
Because it's turned off at 10, so that's your starting point. You've been trying to find the time when all the snow's melted.
Okay, I like that. We're gonna have to figure out what goes there. If we want all the snow to be melted, we want our total volume to be 0. So we want this to be 0 in the end.
So, well, at 10, the added equation is 0, so you don't have to worry about the losing. So we need to figure out how much snow is there and the rate at which it's melting.
Okay, so amount at time 10, like how much snow is on the mountain, and then we need to subtract what? What is this integral going to tell us? If we want our total to be 0. How much we have minus how much we lose, right, should give us a total of 0. So amount lost. Which function are we going to use for the lost? M of t. Okay. Can we figure out the amount of snow at time 10? Yeah? How? It's kind of similar to part D, right? How much snow is at time 5? Yeah? We're going to do the same thing, but how do we have to change this for time 10?
Just
Upper bound of 10. Okay, so we can conveniently, I mean, you could type it in all at once again, but if you hit second entry, it'll bring up the last item that you typed in. So we'll arrow over, and we're just going to change the 5s to 10s. So we'll get 183.193. Right, so I'd say that's an equation. I mean, we have an equal sign. We're showing the left has to be the same as the right. We don't have to solve it. We could if we wanted to, but we don't have to solve it. Griffin, were you going to have a different setup, or?
No, I mean, it was basically the same thing, but I was going to say how, just to make it less space on the paper, like I didn't actually solve out to get the 183.
Yeah.
But I just combined the two integrals, just made it s of t minus m of t. So like, I had, my thing was 0 to 10, and then in parentheses s of t minus m of t, and then dt, instead of having both.
Like that?
Yeah.
So you had this one instead of this one?
Yeah, I mean, I'm pretty sure, well, plus 50.
Plus 50? Oh, that would have been fine. Okay, so if you wrote all of this out before calculating the number, that would suffice too. That's perfectly fine. Okay, it's still an equation. So you'd have all of this, and then minus the integral from 10 to k like we have here equals 0. That's fine too. Okay. All right. Let's take a look at average value a little bit further. This one wasn't necessarily all about average value, but notice how at least one piece of it had that component to it where you had to understand what the notation meant in terms of the problem. So whenever you see that 1 over the difference of the bounds out front, I'm hoping that's eventually just going to be a clue for us, like average value. So whatever this integral function represents, just put the word average in front of it, and there's your meaning. Okay, average value. Let's try more of a functional based one. Let f be the function defined by this piecewise. Find the average value on the closed interval from 0 to 5. Can we think of our setup? If we want the average value of f, we'd have to use the f of x function. Our interval is from 0 to 5. And since we want the average output, we need 1 over the difference of the bounds. So I'd say there's an integral that partially represents the statement. The question is, which function are we going to use for f of x? How are we going to use both? You have an idea, Megan?
Can you
Here?
change that interval from 0 to 3 and 3 to 5?
So notice how we need the overall interval to be from 0 to 5, but within that interval we have two separate ones. So we're going to need 1/5, we're still going to need the 1/5, but we're going to change this integral from 0 to 5 into two separate integrals. One from 0 to 3 of the square root, and then one from 3 to 5 for the line. What would we have to do to those two integrals to get the overall interval from 0 to 5? Add them. Yep. Basically, the area under all of f from 0 to 5 is the same as the area from 0 to 3 added to the area from 3 to 5. That was one of our properties. All right. So for time purposes, we're just going to type this in and see what we get. Okay, I know we could work backwards by hand by the linear function. We haven't quite talked about how to work backwards by hand from a square root, but we will be getting there by the end of the year. So for now, we'll just go ahead and type it in and see what happens. Alright, so I found my integral values first, and then I divided by the 5 that we had out front and got 1.333. 3. Alright, so that's telling us that on this interval from 0 to 5, the average y value, the average output, the average answer from both of these functions, like when used together, is 1.33333. So some y values are more than that, some y values are less than that, but this is your average. Okay, maybe we'll draw a little picture of it in a second. Since we're dealing with piecewise functions, I thought it would be beneficial for us to maybe review some things that we've done previously this year. Can we prove that f of x is continuous at 3? What does it mean to be continuous?
It does have to be the same value at
Okay, so what do you mean by the same value? That kind of sparked a light bulb in some people. Go ahead, Griffin.
The limits on each side of 3 have to meet up.
Okay, so the limit exists. We have to check that. Yeah? The point exists. We have to check that. And what Christian said, they have to be the same. So point equals limit. All right, let's do each one of these. Do we have a point value at 3? How can we find it? Plug it into which function? The top one. Okay, so our point exists and it's 4. How can we find a limit value?
From the right, from the left.
From the left and from the right. Okay, so if we plug in 3 into the left-hand side, we already know we're going to get 4. If we plug in 3, okay, so I'm going to say left was 4. If we plug in 3 to the right equation, no wait, this should be 2. My bad. I didn't take the square root of it. Alright, if we plug in 3 into the right equation, we'll also get 2. Does the limit exist?
Yes.
Yes. Do the point and the limits match?
Yes.
Yes. 2 equals 2. Okay? So we are continuous at 3. Alright, so we know that at this spot of 3, there's no hole, there's no jump, there's no asymptote. They are connected somehow. How can we prove that this is not differentiable? Can we think about what the word differentiable might mean?
Their slopes have to be the same at the point.
Differentiable, there we go. If it's differentiable, we're talking about a slope. So if it's not differentiable, there's no slope at that point. Meaning, Addison, you started saying? Sharp points, endpoints, vertical slopes. Okay, so those, if you don't have any of those, then you are differentiable. That means if you're not differentiable, you have one of those 3 things happening. So basically, for not differentiable, we need to show how the slope from the left does not equal the slope from the right, because of that word not in there. Okay? Can we find the slope of the left?
Yes.
Yes. How would we do that?
You just plug in 0 and 3 and then 5 points to find the slope.
That's your average slope.
Oh wait, you can take the derivative.
We're going to take the derivative of it.
Plug in 3.
Yep, that's our chain rule.
So you can-
Alright, so there's our derivative, aka slope from the left. We need to show that this does not equal the slope from the right. The slope from the other equation is close. -1. Okay, and if we plug in 3 for x, so the square root of 4 is 2. Since it's a negative power, it would change to 1 over 2 to the bottom of a fraction. So 1 over 2 times another 1 over 2, we'll get 1/4. Clearly, they're not differentiable. So if the slope from the left is 1/4 and the slope from the right is -1, what's happening at this spot of 3? Sharp point, end point, vertical slope. Sharp point. So I think if we were to actually graph this piecewise function, we'll go all the way to 5. Let's see, if I plug in 0 into that square root function, I'll get 1. If I plug in 3, I'll get 2. And then for the line, if I plug in 3, I get 2. If I plug in 5, I get 0. Do you know what? I'm gonna count these by halves, just so it's better. So 0, 1, 3, 2, 5, 0. So to connect these first 2 points, it has to be in a square root shape. So that curve to the side. The other 2 points are from a linear function, so we'll do that. So notice how they are connected, meaning they are continuous, but we have a sharp point there, meaning not differentiable. This average value that we found, 1.333, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, Does that kind of look like to be in the middle of our graph? Okay, so all of these y values and higher than it, and all these y values lower than it are averaged together, and we would get 1.333, something in the middle in terms of an output. Okay, so I think that's another good visual for us to have. All right, we're officially done with Unit 6. So my goal is Monday we're going to have kind of a board practice day with all this integral stuff. And then Tuesday, I believe, is going to be another free response day. But after that, we're going to be getting into the partner quiz and the unit tests, okay, for this unit. So coming up next week, maybe into the following. Yeah.
Are we hitting like Wednesday quiz and then double Wednesday and then Thursday and Friday? Or is that review?
I had, so this was my plan. What's the 4th?
Wednesday.
The 4th is Wednesday, so that's quiz. The 5th would be your review day. So then your test is going to be Friday and following Monday. Okay, it's going to split the weekend, unfortunately. And then one more unit. Yep.